Hi all, this is Clarice here. We are here for the sixth problem solving section for the course Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. So this week has been predominantly focused on electron spectroscopy of atoms, and we slightly have started with the diatomic molecules. In this problem solving session, I will only be dealing with the questions associated with atomic spectra, and I'll be going over a couple of problems on term symbols of atoms. Yeah. So yeah. So we have been I think in the last week itself it has been introduced to how a term symbol look like. So a term symbol look like can be denoted like can be denoted as 2s plus 1 L subscript j, this just like this, 2s plus 1 L j, and we'll be slightly introducing to what are these every terms means. So L denotes to total orbital angular momentum, J denotes to the uh, total angular momentum, and S denotes total spin angular momentum. Okay, and depending upon different values that we obtain for L, the L that is denoted in the term symbol can have different alphabets associated with it. If the L value is 0, the associated alphabet is S, and if the L value is 1, the associated alphabet is going to be P, and if the L value is 2, the associated alphabet is going to be D. If the L value is 3, alphabet is going to be S, and similarly for if the L value is 4, it is going to be G. I hope all of you can hear me properly. Yeah, if you are not able to hear me, can you please question in the chat box? Yeah. So L corresponds to the total orbital angular momentum. So in case if we have more than one electron present in the system that we are present in the atom that we are looking for, then we have to calculate the L value. So L value is defined as L1 plus L2 till L1 minus L2. So it depends upon where all your electrons are occupied, which all orbitals where your electrons are occupied. So depending upon that, you have to give the values. So if your electron is occupied in s orbital, then your L1 is going to be 0. If your if your if you have another one more electron occupied in the s orbital itself, then your L2 is going to be 0. So which means your capital letter L can only have one value, which is 0, which is L1 plus L2. And if you negate L1 minus L1 from L2, it is going to be 0. Okay, so in this the first question is to find the terms that can arise from the following configurations. So the first one is D2. So which means you have 2 electrons in d orbital. Oh, I see. One second. I'll just try to reconnect. The voice is breaking. How is it now? Is it still breaking or is it fine? Hello. Hello. Am I still audible? Okay, fine. Great. So yeah, we are talking about the terms that can arise from the configuration D2. So the L value corresponding to a d orbital is going to be 2, right? So L value corresponding to S is 0, P is 1, D is 2, uh, F is 3. So let's consider these things, these values, and yeah. So if you're when you have two electrons in the orbital, your L1 is going to be 2 by 2, and L2 is also going to be 2 because your other electron is also in the d orbit. So your minimum value that L can adopt is going to be L1 minus L2, the absolute value of L1 minus L2, which is 2 minus 2, which is 0. So your L values can be L1 plus L2 till 0. So this L1 plus L2 is 2 plus 2, 4, 3, 2, 1, 0. Okay. And the corresponding terms that it will, the corresponding symbol that it will, that it denotes to is going to be G, F, D, P, S. Okay, so a D2 configuration can have 5 different terms arising from G, F, D, P, S. In this question, we just need to find what the terms. We don't have to give the complete expression of the terms. Okay, I am only going till the total orbital angle. Okay, I think it's taking slightly longer to load it. Okay, so the second configuration was was P3. So let's do it for P3. Your L1 is equal to L2 is equal to L3 is equal to, because all of them are in p orbital, the L value corresponding to it is 1. So what you're supposed to do is, what happens when two electrons coupling. For two electrons coupling, you will have a total orbital angular momentum L prime. Let's name it as L prime. Yeah, L prime, which will come from L1 plus L2 till L1 minus L2. So in this case, it is 1 plus 1, 2, 1, L1 minus L2 is 0. Okay. Then what happens is, so you can have three different values of L prime. So for L prime is equal to 2, you will have, and the L prime 2 is coupling with L3, which is equal to 1. So you can have an L value of L1 plus L2. Sorry. Yeah. L prime plus L3 till L prime minus L3. So this is 2 plus 1, 3, 2, L prime minus L3 is going to be 1. So three values that can arise from L prime 1 and L3 1, L prime 2 and L3 1 is going to be 3, 2. Then for L prime is equal to L prime is equal to 1 and L3 is equal to 1. L values can be L prime plus L3 till L prime minus L3. This is going to be 1 plus 1 is 2, 1, and 1 minus 1 is going to be 0. So 2, 1, 0. And what happens when L prime is 0 and L3 is 1? So L can be L prime plus L3 till L prime minus L2. So this is going to be this is going to be 0 plus 0 plus 1 is 1, and that is the only term that it can arise to, right? So yeah, so for this particular system, the term symbols that can be that can come up will be 1 3, 2 from these, 1 from this and 1 from this. So 1 2 from this and the other 2 from this. That's what has come up in these two places. And we have two ones, one coming from when L prime is 2 and L3 is 1, and the other one is from this one, L prime 1 and L3 1, and the other one coming from, the last one coming from L prime is equal to 0. So 3 1 and you have 1 0. So there will be one F term coming from here, and 2 D terms, and there are 3 E terms and 1 S term that will be coming for this particular electronic configuration. Okay, we have 2 more to solve. Let me have one more blank slide here. The other 2 are F1 D1 and D3. So we are looking at F1 D1. So in this particular case, L1 is going to be F1. F1 corresponds to 3 and D corresponds to 10. L2 corresponds to 2. This is from D and this is from F. And your L value can be 3 plus 2 till 3 minus 2. So this is going to be 5, 4, 3, 2, 1. 3 minus 2 is going to be 1. Okay. So for F1 D1 electronic configuration, you can have only one. You can have 5 different L values, and this corresponds to so it can have 5 different values, and the last one is D3. 5 corresponds to H, 4 corresponds to G, and this corresponds to F, D, and for D3 configuration, it's again going to be a little complicated. So you have L1 is equal to L2 is equal to L3 is equal to 2. You can follow the same protocol that we followed for P3 configuration here. I won't be doing it here at this point of time. Maybe you can try it by yourselves. If we have time towards the end, we can come back and always do this. Do the last question here. Let me move forward. So it's going to be similar. We have to follow the same treatment that we have done for P3 electronic configuration. Okay, the next term that we have found that how to calculate total orbital angular momentum, and now we will get to know how we calculate the spin angular momentum. So that which is also there in the term symbol, which is here in the superscript 2s plus 1. So L C. So S is the spin angular momentum, and it can be calculated, total spin angular momentum, and it can be calculated by taking summation of SI, where SI is the angular moment, spin angular momentum of individual electrons. So the SI can adopt S can adopt different values ranging from summation of SI from summation of SI minus 1, summation of SI minus 2 till 0. So let's have a okay. Let me go over if I give you a physical intuition of how these values can be adopted. These different values can be adopted by total spin angular momentum by using this question. So suppose we have an atom which has two electrons in its in different orbitals. So basically, it have consider you have S1 T1. The electronic configuration is S1 T1. So it has we have an atom which has electrons in different orbitals. Now we have to give possible values of total spin quantum number and what is the multiplicity in each cases. Multiplicity means 2s plus 1. So okay, let me just write it explicitly here. Multiplicity is 2s plus 1. Okay. So for this particular system, if you have a s orbital, consider this is S and this is the P. So both electrons can orient in same direction or it can orient in two different directions. Since it is in two different orbits, it doesn't have a problem if both of them orient in the in plus 1 by 2 direction, or if one is orienting in minus 1 by 2 and the other one orienting plus 1 by 2. So in this particular case, the S value can be, if you just add these two, this is going to be 1, and if you add these two, this is plus 1 by 2 minus 1 by 2, it's going to be 0. So your total spin angular momentum is going to be 1 and 0. And if you apply this equation, for example, so if you have an S, if you have to calculate using the equation given here, what you have to do is you have to summate Si. So you have two electrons, so it's going to be okay, 1 by 2 plus 1 by 2, just adding two spins. So it's going to be, so you can go from S equal to summation of Si, which is 1, you can go till 0. So the two values that it can adopt is going to be 1 and 0 for when you have like two electrons. So what happens when you have three electrons in different orbitals? I'll also explain what happens if we have two electrons in the same orbital itself. So in case if you have two electrons in S2 itself, you have two electrons in the S orbital itself. So this is your S orbital. The two orientations that the spin can adopt, the only one particular orientation that both spins can adopt is one being in plus half, the other being in minus half. So your S value is going to be 0. So this is when both of them are in same orbital. So let's have a look at what happens when three electrons are in different orbitals. So we have three electrons in different orbitals. Okay, so we have, consider you have a S, you have 1s, 2s, 2p, and you have 1 electrons in all these three orbitals. So what happens to your S value? So according to the formula, you can have Si minus 1 till 0. So you have, since you have three electrons, the summation of Si is going to be 1 by 2 plus 1 by 2 plus 1 by 2, which is going to be 3 by 2. So this is 3 by 2, 3 by 2 minus 1, and 3 by 8 and 0. So it's going to be 3 by 2, 1 by 2, C. Now let's have a physical understanding of how it is what sort of a orientation that electrons are adopting in these particular S value cases. So, so in this particular case, all the three electrons are orienting in plus 1 by 2 direction. So your S value is going to be 3 by 2. 1 by 2 plus 1 by 2 plus 1 by 2, which is 3 by 2. So think about one of the electrons being in the opposite orientation. Now it can the electron that is in opposite orientation can be in 1s or in 2s or in 2p. So I'm just giving it in 2s just for a just as an example. So in this particular case, this is plus 1 by 2, this is minus 1 by 2, so this will cancels out and makes it to 0, and you have basically you just add all these three orientations, which is like plus 1 by 2, minus 1 by 2 and plus 1 by 2. The addition will give you 1 by 2. And the other one is, okay, yeah, since you have odd number of electrons, um, yeah, since you have odd number of electrons, I don't think so you can go till 0, because it's simply because you can't have it orientationally possible. So you may not be able to go till 0 if you have something, if you have odd number of electrons. Okay. Uh, then the next part. Okay, sorry. Sorry, there's some problem. Okay. I don't know why I'm not able to erase. Okay, that's fine. So yeah, we won't be able to have 0 if we have odd number of electrons. So we are at till finding what are the possible values of total spin angular momentum if we have 2 electrons or 3 electrons in different orbitals. Okay, now we have to find what is the multiplicity in each of the cases. So in this particular case, the multiplicity is going to be 2s plus 1, right? So it has s value associated with, if the s value is 1, then 2s plus 1 is going to be 3, and if the s value is 0, it is going to be 1. This is multiplicity. Two s plus 1. For s value equal to 1, it is going to be 3. For s value is equal to 0, it is going to be 1. So in case if you have s value as yeah, if you have in this particular case your multiplicity 2s plus 1 is going to be for 3 by 2 it is going to be mm, it is going to be 2 into 3 by 2 plus 1, and you so it's going to be 3 plus 1 4, and this is so the multiplicity associated with these S values are 4. So we are sort of done with this particular question. So the third term, we have seen what is how to calculate L, how to calculate S. Now we are here to here to calculate what is J. J corresponds to total spin angle, total angular momentum. So this comes as the subscript in the term symbol. So here we have been asked what information of the does the term symbol 1 lead to is provide about the angular momentum of an atom. So yeah, so let's deconvolute all the different angular momentums from the term symbol 1 lead to. So L value is for for a symbol L, D, the L value, the total orbital angular momentum is going to be L is equal to 2, and for since the multiplicity is equal to 1 is equal to 1, so we can say that 2s plus 1 is 1, which implies your S is equal to 0. So your total spin angular momentum is equal to 0. Okay, the total angular momentum is L plus S till L minus S. So if you have, it starts from L plus S, goes through L plus S minus 1, go till absolute value of L minus S. So since we already have what is L value and S value, we can find that the J value here is going to be 2, which is which can be either, I mean, both L plus S or L minus S. And so the total angular momentum is going to be 2 for this particular atom. We can also deduce the electronic configuration. I mean, we can also uh, have an idea of what sort of a electronic configuration that 1d2 is corresponding to. So if you have 1d2, you you and the spin angular momentum, total spin angular momentum is 0, which says that you have uh, you have even number of atoms, is even number of electrons, and since your total orbital angular momentum is 2, uh, that also sort of says that your uh, that says that uh, you have your electron in either p or d orbit. So since the total spin angular momentum quantum number S value is your S value is 2, this is even electrons, and your L value is 2. So it says that either you have L1 is equal to L2 is equal to 1, or L1 you have only one electron in d orbital. This is not possible because you have even number. I mean, according to the total spin angular momentum, you either need two electrons in the in the um, you you at least need two electrons to have s equal to 2. So the most probable uh, probable configuration will be with L1 is equal to L2 is equal to 1. Yeah, so it can be a configuration like that. So this is something which we can deduce from the term simple. It's just not P2 which can have 1D2 value. Um, if you have L1 is equal to 2 and L2 is equal to 0, in that case also you can have, in which case it is D1 S1. In that case also you can have a similar term symbol value. Yeah, that's all I have to tell about this particular question. Now let's so these are the information that we can deduce from a term symbol given for a particular item. Uh, now I will be explaining about how can we come to a term symbol given a electronic configuration. So the first problem is to find the term symbol arising from the ground state configuration of sodium atom. So for sodium ground state, it is going to be neon. Yeah, it's going to be neon 3s1. So we have to consider that we have only one electron in S1. So we just have a S1 configuration. So your L value is going to be, you just have only one L. So because there is only one electron at the outer orbital, so L value is going to be 0. So your capital L is going to be 0, and your S value is going to be 1 by 2 because you just have only one electron. So your capital S value is going to be 1 by 2, and J value is L plus S, which is 1 by 2. So if L is equal to 0, it corresponds to S, and let's find what is the multiplicity 2s plus 1. This is going to be 1, right? If S is equal to 1 by 2, 2s plus 1 is going to be 1. So it is going to be, so we have 2s plus 1 J, sorry, it's going to be 2s plus 1 L J, and L is S here, so S, this subscript is going to be 1 by 2 because the J value is 1 by 2, 2s plus 1 is 1. So the term symbol is going to be, sorry, this is going to be 2. So 2 into 1 by 2 plus 1 is 2. So this is going to be 2s 1 by 2. Okay. Now the second one is going to be the find the term symbol for the ground state configuration of fluorine atom. So a fluorine atom is He 2s2 2p 2p 5. So you have how many unpaired electrons? Can also write something like this as neon 2p minus 1, and yeah, it's basically an absence of one electron, and your L value is going to be one, and which makes your total angular momentum to be 1, and S value is 1 by 2, and you are just since we need one more electron to finish off the fill the p orbital, 2p orbital. The total spin angular momentum is also going to be 1 by 2, and yeah, the j values which are possible is going to be L plus S, L plus S minus 1 till C, L minus S, and L plus S is going to be 1 plus 1 by 2, which is 3 by 2, so 3 by 2 means 1, and L minus S is going to be 1 minus 1 by 2. So this is also equal to 1 by 2. This is also equal to 1 by 2. So it's going to be 3 by 2, 1 by 2, and 3 by 2 and 1 by 2. So the corresponding term symbols for a term symbol will depends upon the L value. Here the L value is 1, which corresponds to P, and the spin multiplicity is going to be 2s plus 1, which is 2, and the term symbol is going to be 2p 3 by 2 and 2p 1 by 2. And now we need to find the term symbol associated with the excited state configuration of this particular excited state configuration of carbon. So it's going to be the given configuration is 1 is to 2 is to 2p1 and 3p1. Yeah. So our L1 is going to be, since it is in 1 is going to be in 2p orbital, L1 is going to be 1, and the other is also in another p orbital, so it is going to be it's going to be again 1. So the total L value, the total orbital angular momentum is going to be L1 plus L2 till L1 minus L2. So this is going to be 1 plus 1, 2 till 0, 2, 1 and 0. 3 L values that are possible are 2, 1 and 0. This corresponds to the symbols D, P, S. Okay. And the S value, the total spin angular momentum, capital S, can take summation of SI minus 1. So here we have 2 electrons, so it's summation of SI is going to be 1 by 2 plus 1 by 2, 1 and 0, and the 2s plus 1, the multiplicity can be um, 3 and 1, and the total angular momentum L, so J can have values from L plus S to absolute value of L minus S. So this is going to be so for L is equal to 2, which corresponds to P, the J value can be L plus S to L minus S, where L is 2 and S is L plus S is 2 plus 1, till L minus S is 2 minus 1, so it can have values from 3 to 1, and the symbols corresponding to that is going to be um, 3, 3, 3, 2, 3, for L is equal to 2 and S is equal to 0. The J can have values from L plus S to L minus S. Here it is going to be 2. It can have only one value, which is 2, because the S value is 0 here. So the term symbol corresponding to this is going to be 1, 2. And we have 2 more values of L. So for L is equal to 1, if the S is 1, then J can have values from 1 plus 1 to 0, 0. 2s plus 1 is going to be 3. So L is equal to 1 corresponds to P term. So the different term symbols that it can have is 3P2, 3P1, 3P. For L is equal to 1 and S is equal to 0, the different J value, we can only have one J value, which is 1, which is L plus S or L minus S. Both of them are going to give rise to same J value, and it is going to be 1. L is equal to 1 corresponds to P term, and S is equal to 0 will give rise to a multiplicity of 1, and the corresponding term symbol is going to be 1p 1p1. This one is coming from 2s plus 1, the multiplicity, and this subscript 1 is coming from the total angular momentum J1. And for we have one last value of L, which is L is equal to 0, and if S is equal to 1, the J value is going to be, we can have only one particular J value, which is 1, and L is equal to 0 corresponds to a term S, and S is equal to 1 will give rise to a spin multiplicity of 3. So this is going to be 3S. And for L is equal to 0 and S is equal to 0, the J value can have, J can only adopt one value, and the L is equal to 0 corresponds to its term S, and S is equal to 0 will correspond to a spin multiplicity of 1. So this is going to be 1SC. So this particular excited state configuration of carbon atom can give rise to a couple of three different L values, three different L values, and every L value can have two different S value, which give rise to two different spin uh, spin angular spin multiplicity, and depending upon the L and S combinations that we are taking, it can have different J values. So we have around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 term symbols arising from this excited state configuration of carbon. Now let's come to the selection rules associated with the electronic transitions in many electronic atoms. So the different selection rules that has been covered in the class are the spin selection rule, which says that if the transition is only allowed when the delta is the change in total spin angular momentum is going to be 0, and also if the change in total orbital angular momentum is either 0 or plus or minus 1, and the change in total angular momentum can change in total angular momentum is is only allowed to have values of 0 or plus or minus 1. So we've been given a couple of transitions, and we find uh, what are the transitions are allowed. So the first one is 3D2 to 3D1, where we can see that del so okay. Let me also elaborate on. So 2s plus 1 Lj. So if we find 2s, if the s values delta is going to be 0, then if delta has to be 0, then 2s plus 1 value also should be the change in 2s plus 1 is also should be 0. So if we are having a transition from between spin multiplicities 3 to 3, it's spin allowed. And let's have a look at the L values. So the L value here is 2, here the L value is 1, So the delta L is going to be 1. So this is in, if we when we consider the orbital angular momentum of the system, the transition is again allowed. Now let's look at the J values. So if here J is going from 2 to 1, so delta J is equal to 1, which also follows the selection rule associated with total angular momentum. So this is also allowed based on the total angular momentum. The second one is 3p to 2, 1 is 0, and write it in expression. 3p to 2, 1 is 0. So delta S is not equal to 0 because the multiplicities are not the same. 2 is plus 1 is 3, 2 is plus 1 is 3 here, here it is 1, which will not uh, which is not following the spin selection rule. So this is a spin forbidden transition, and the p value is, the L value is 1 here and it is 0 here. So delta is L is 1. It follows the angular selection rule associated with the total orbital angular momentum. And J value is 2 here, J value is 0 in 1 is 0 term, so which makes delta J to 2. This is not following the total angular momentum selection rule, so this is also forbidden based on this particular. So this particular transition is forbidden or not allowed. Third one is 3F42, 3D3. So 2s plus 1 is 3 in both cases, so it is allowed by the spin selection rule. The L value is, for F it is going to be 3, and for D it is going to be 2. So this is also allowed because your delta L is 1, and the J value is 4 and 3. So your delta J is equal to, your delta J is equal to 1. So this is also allowed in terms of the total angular momentum rules. So overall this transition is, so we just have to find out what are the so if you have given a particular transition, uh, we have to find the we have to find what is 2s plus 1, what is the L, what is the J. The 2s plus 1 should not change between the two states that the transition is happening, and the L value L values should change either by 1 unit, or it should not have any difference. And in case of J value can have delta J value should be uh, plus or minus 1 or 0. Otherwise, the transitions are forbidden. If at all it doesn't follow any of these rules, one of these rules, it is not allowed. So yeah, that's all I have to discuss with you today. If you have any particular questions from the if you have any particular question from the questions that we discussed today, please raise me. Otherwise, we can. Okay, let me briefly go over the problems that we covered in today's session. So, we first discussed um, how to calculate the total orbital angular momentum and how to come up with the different term symbols. And then we okay, so if we have two electrons, we have to consider one of the L values corresponding to be L1, the other L value to be L2, and depending upon different electronic configuration, we can get different term symbols. And yeah, for a particular configuration we can have different term symbols associated with it. So for example, for T2 we can have different L values ranging from 4, 3, 2, 1 and 0. This is and for when you have more than more than two electrons, first you have to consider the coupling of two electrons. Then you have to treat the output of the outcome of that L value, um, outcome of that L value as uh, one of the individual orbital angular momentum, and consider its coupling with the other um, consider its coupling with the other uh, electron. And yeah, we have also seen how it is being done for F1 B1. You can try how it is being done for P3. It follows the same protocol as P3. Then we also have covered how to calculate the spin angular momentum, the total spin angular momentum of the system. And yeah, so it can have values between summation of Si uh, to 0. Uh, then we yeah, then we had gone over how to what can we infer about the angular momentum of an atom given a term symbol, and we also have seen how to find the electronic configuration given a term symbol. What all electronic configurations can uh, give rise to this particular term symbol. Then we've uh, come across with how to write the term symbols for given a electronic configuration. So we have done it for sodium and fluorine, which are for its ground configurations, and we also have uh, done it for the excited state configuration of some one particular excited state configuration of carbon. So this particular excited state configuration of carbon atom can have 10 term symbols. Then we have seen how the selection rule works, and whether the given transitions are whether these transitions are allowed according to the selection rules. That's all I have to discuss with you today. Let me know if you have any particular questions. Okay, thank you very much for joining. If you don't have any questions, shall we end the session for today?